But the idea of the valley of beta stability is actually shown on page 68. There is a relationship that was known from the 1930s. It's called Weizsäcker's semi-empirical mass equation. And what is done here is they're actually, in figure 414, they are actually looking at a stable isotope of ruthenium. And I don't know what the, I guess it's everything in there. Yeah, these are all isobars. So it's ruthenium-99. And there are a variety of other elements that are actually going to decay ultimately to ruthenium-99. So if you look at this diagram, you'll notice on the right-hand side of the diagram, we have a bunch of positronic decays, and on the left side, we have a bunch of beta decays. And then there are these steps. So basically, what the semi-empirical mass equation does is it relates mass or energy. If we plot, it could be energy in your book, it's energy, but it wouldn't be the same thing if we plotted it as mass. So it plots energy this way, and it plots Z number, atomic number, on the x-axis. So what we've got is we put on the abscissa these elements: zirconium, niobium. So this is atomic number 40, 41, 42 is molybdenum, 43 is technetium, 44 ruthenium. This is the stable one. And then we've got some higher ones: rhodium, palladium, and silver. Rhodium, palladium, and silver. So these are all of the isobars in that range for A equals 99. Zirconium 99, niobium 99, molybdenum 99, technetium 99, ruthenium, the stable one, and so on. So we get to these decays through, these are a series of beta decays. So this is a beta here, and then we've got another beta going here, and then there's another beta, and these get higher and higher, and then there's one up here. So we've got a beta going down here, and a beta going down here, and another one going here, and so on. And you can see each one of these then coming down to here, and then so this is all beta decay on this side, and then we have positronic decay on the other side, and you know, we're going to start up here, and we're going to be so we've got up here is the silver, and the silver is actually at a higher energy level, and then that's going to come down, and it's going to go to palladium through a positronic decay, and then to rhodium through another positronic decay. That's going to come down to here, and then finally that's going to decay back to ruthenium. Well, what Weizsäcker actually found was that this kind of a decay, if you looked at this, you plotted this out, it approximates a parabola. And you can use these parabolas to actually show this semi-empirical mass relationship, relationship between mass and between Z number and mass or energy. So this is shown in a three-dimensional way. So there's a 3D chart. Here you're plotting M, which you were plotting in the two-dimensional one. I'm sorry, you were plotting mass. Well, this is plotting mass per nucleon, and it's also plotting Z, and it's also plotting the neutron number as well. So it's plotting all three of these things. And I can't, you'll have to, hopefully you have a book by now, you'll have to look at the figure on page 69, but you'll see that this thing overall in 3 dimensions, it forms a valley of stability down here. So this is one of the things that we can get out of this, is we can find that we know that all the stable elements are going to lie down, all the stable isobars are going to lie down at the bottom of the valley for these things. So we've got, there's a table 4.2 on page 69, and it shows various isobars with atomic mass of 104, indium, cadmium, silver, palladium, rhodium, ruthenium, technetium, molybdenum, and niobium, and it shows you the decay modes. And you'll notice that in this particular case, you actually have two, where here there was one, this went to one stable isobar. Here in this particular one, there are two stable isobars. So for A equals 104, there are two stable isobars. Above that, we have principally positronic decay, and below that we have another one that's positronic, and then electron capture, and then there's a bunch of beta decays below that. So you can see which side is positronic, which side is beta. This, like I said before, was the positronic side here, and you can see that for these particular isobars. And one of the interesting things also that occurs here is something that's now known as Maddox rule. And this just basically says that if you look at these isobars, the ones that are adjacent, you'll never have two stable isobars next to one another. So you can see on page 71, there's a couple examples of this that are actually given on page 71. Simplified decay diagrams representing all possible pathways with mass with an even number atomic mass. So with an even atomic mass, you can have one stable isobar that's going to be odd. You can have odd. This is not a, when the mass number is even, you can start so you have odd number of protons and odd number of neutrons, but you still get an even number. Or you can be even, and if you're even, you can have only one. You can have one stable even type of configuration, or you can have two stable even configurations, or you can have three stable ones. So they look like either like. Let me erase this. Okay, so you could either have this kind of a situation where your stable isotope is here, your stable isobar is there, and then you've got something decaying up here and something up here, and this is odd, even, and it goes like that, and you've got something that goes like that, and they're both going to. So this is the you just have one stable odd here, or you can have a stable even, which would look like this. And again, this would be your stable, and your parabola would sort of look like that. You could also have the possibility of, again, something that looks like this. There's now two stable ones. So you've got here, and one that's unstable, then another stable one here. But in every one of these cases, what you notice is that the unstable ones are never, if there are two stable ones, they're not right next to one another. The two unstable ones, they're not right next to one another either. Here's another one. This is the one that has three stable. So you've got one stable here, then an unstable, then a stable one there, and another unstable, and a stable one here. So there are three of them. So the idea is that they alternate, stable, unstable, stable, unstable, and that is really what Maddox rule is trying to show us. Let me see how much is left in this book. Can we actually get through it today? Doubtful. Well, there's about another 4 pages. I'm just going to go through this, and then I will allow the powers that be to probably shorten this a little bit, and we'll see how that actually comes out. But this might be, I don't know whether this will be 1 or 2 exams, but at least you won't have to listen to this as a single hour-and-a-half lecture. Maybe we'll split it up so it'll be 2 45-minute presentations and maybe just one exam. All right, so let's see. The next section has to do with what are known as isomeric transitions. So, okay, so what we have, we can have isomers, 2 nuclides with the same number of protons and neutrons, but they can be in different energy states. We've already seen that. We've seen that with things like technetium, where we had one that was at a higher energy and one that was at a lower energy. Sometimes these things will emit gamma photons. Sometimes they undergo what is known as an isomeric transition, and that's what I want to talk about right now. So in isomeric transitions, what we sometimes get are, where we've got a higher energy going to a lower energy. We might sometimes, in many instances, we might just emit a gamma photon, but in other instances what will happen is a process known as internal conversion actually occurs. And in internal conversion, what actually happens is an electron gets booted out. We've seen that before. We saw that with Auger electrons. But these are different than Auger electrons. And the difference, well, let's see, before I get to this, wait a minute. This could be a little confusing. Let me just back up for a little bit. I want to look at figure 4.18, which actually shows a metastable state of xenon 125, and it's decaying to the stable state of xenon 125, and it's doing it by emitting a couple different gamma photons. So this again is a multiple photon route. We saw this earlier in the chapter. That's why I didn't want to skip this again, because I don't really think the first time they really went into detail when we were talking about multiple. Let's see, where was that? This is back on page. This is a very long chapter, so it's kind of hard to find stuff in here. Definitely, I think the longest chapter in the book. But there is, let's see if I can find this here, where it's talking about multiple decay. It's in the, I guess in the section on multiple decay modes. I don't remember exactly now where I saw it, but it does talk about, no, it's not the multiple decay modes, it's the, I don't see it right now. Well, anyway, it doesn't really matter. I guess this is xenon 125, the metastable, and you'll notice that off to the right hand side it actually is showing you the spin, which is 9/2, and there's a negative sign next to it. These signs here, by the way, there's also a 3/2, and that one has a positive. So these are spin directions, positive, negative spin directions. And I'm not going to go into what these fractions represent right now. It's kind of complicated. They have to do with orientations, but the point is that you can have spin 1/2, spin 3/2, spin 9/2. It turns out that this transition, going from 9/2 to 3/2, is what is known as a spin-allowed transition. So this is a transition that has some reasonable probability of actually occurring, and that emits a gamma of 140 keVs, 1,000 electron volts, and then there's another one that is a gamma of 112 keVs, and that goes all the way to the ground state of xenon 125. So you've got these two. Turns out that this transition going from 9/2 to 3/2 is allowed, from 3/2 to 1/2 is allowed, but you notice that there is no transition that goes from 200, that produces a 252 keV electron. It only occurs in these two steps because going from 9/2 to 1/2 is a highly improbable type of transition, and we say that it's not allowed, or it's been forbidden. So this is a forbidden transition, so we don't see that at all. And what we do see when a nucleus changes from one spin state to another, energy is always being released. So you've got going from here to here, energy is being released as a gamma photon. Going from here to here, energy is being released as a gamma photon. Sometimes, though, it's not being released in the form of a gamma photon. It could be released by a K-shell electron being actually emitted. So when that happens, we call that process internal conversion, and we call the emitted electron. It usually, most likely, the electron is going to come from the K-shell. It could come from other shells as well, but as we're going to see momentarily, the K-shell is the most probable. And we would write that as K-INT-COV, which is K internal conversion. So that's just telling us that the if we see this designation, it's telling us that we've emitted that K electron. That's where that excess electron bonding energy is going to. The kinetic energy, the conversion electron, is the transition energy minus the electron binding energy. So if we look at tellurium, this is another isobar of xenon, but this time we're going to look at tellurium 125. So tellurium, in an excited state, tellurium 125. What you'll notice is that there are actually 4 different possibilities. I'm on table 4.3 on page 73. There's a 6.66% probability of a gamma emission occurring. So this could drop down to the ground state of tellurium through this gamma. Loses 35.5 kilo electron volts, and that's a probability of 6.66%. We could have a K internal conversion electron emitted. That's got an 80% probability. We could have an L internal electron emitted, internal conversion electron emitted. That's 11.42% probability, or an M internal conversion electron with a 1.90% probability. And we can actually look on here and see what the energy of each one of those things is from table 4.3, and we find out that that the gamma itself is 35.5 kilo electron volts. The K-shell electron binding energy, therefore, is going to be that gamma energy minus the energy of that internal conversion electron, which is 3.7. So if we subtract 35.5, if we subtract 3.7 from that, we get 31.8 kilo electron volts. That gives us the K-shell binding energy. We want to find the L-shell binding energy. We subtract that from 35.5. That's 35.5 minus 31, again from the table 4.3, and that gives us 4.5 keVs. And the M is going to be 35.5 minus 34.5, or a 1.0 kiloelectron volt binding energy. So we can actually calculate something called the conversion coefficient, which is alpha sub t, and alpha sub t is going to be equal to I sub c, which is actually going to be the number of conversion electrons that we've got, divided by I sub t. And that will be, so our I sub t value is actually, we can actually use, these represent gamma photons, and these represent conversion electrons. So since we don't actually have numbers of these, we can use the probabilities in place of the numbers. So if we look at our table again, and we say that the probability of conversion is going to be the sum of the K internal conversion, the L internal conversion, and the M internal conversion. So we add up 80, 11.42, and 1.9, and then we divide that by the probability. So this is 80 plus 11.42 plus 1.9. This is taken from table 4.3, and then we divide that by the probability of gamma emission, which is 6.66, and that gives us a value of 14. And that will tell us then, so that obviously is showing us that for this particular element, there's a much greater probability of getting internal conversion than there is gamma emission. Okay, and you can do that, you can calculate the conversion coefficients for each of the individual electron shells. So for the K shell, alpha sub K is I sub C, I sub gamma. That wasn't a T, it was a gamma. I'm sorry, I put a T there, it's a gamma. My vision is not very good. And that's going to be, that will be 80 divided by 6.66, so that's 12. For the L shell, it's 11.42 divided by 6.66, 1.71. And for the M shell, it's 1.90 divided by 6.66, only 0.285. So the total value, while it's large, it's 14, you can see that most of that is coming from the K shell, and there's a much lower probability from the L and the M shell. Just to finish this up, a couple other decay modes. Spontaneous fission. There are some radioisotopes that will actually, when they form, they will actually split into two, usually not stable. They may still be radioactive, that actually form from that, although they could be two stable pieces. But they'll form. This is only usually happens with very heavy nuclides, and it's going to be talked about later on when we're dealing with nuclear fission, so we're not going to go into it in any detail here. There's also something else known as cluster decay, again with very heavy nuclides, where instead of an alpha particle being lost, something larger, much larger than that. It could be something like, well, giving you some examples here, it could be a carbon-12 or a carbon-14 or a oxygen-16. The words following that, inter alia, I don't know why he's trying to impress you with his knowledge of Latin, but that just means among other things. So among other particles, you know, you could get any of these small kinds of particles could be actually ejected in cluster decay, and this doesn't happen all that often, but it does occur. And there's also something known as double beta decay. So this is pretty unusual. It happens with neutron-rich, even nuclides such as selenium 82. So what happens in this process is selenium 82 will go to krypton. It goes to krypton 82, and there actually are two beta particles that are emitted in order to produce that. And so you write that as 82 selenium 34 goes to 82 36 krypton, and there are going to be two electrons and two antineutrinos that are produced. So that's a double beta decay. And the very last thing here is a delayed particle emission, sometimes observed for nuclides at the extreme streams of the valley of stability. That is, when we looked at the valley of stability, things that were up here and up here, which were at the extreme ends of this, these are the kind of things where we might see delayed particle emissions. An example is given here for iodine 137, an unusually high and usually neutron-rich form of radioiodine, iodine 137. This is 53. It goes, well, you can write it as a single equation, but as your book points out, you probably might want to write it like this. The first thing happens is it goes to an excited state of xenon. And that produces a beta particle. And an antineutrino. So the xenon is 54-136. Now it's going to decay. And it goes to a stable xenon, which is xenon, I'm sorry, that's 137. It goes to xenon 136. And in order for that to balance out, this has to eject a neutron. So this is a delayed particle emission. First this forms, a beta particle is given off, then the excited state decays by giving off a neutron and forming the stable isotope. So that concludes this entire chapter. Again, I apologize for the length. I don't think we'll ever see anything this long again. I'm going to try to, if I can, try to combine this all into one exam. But it may be, I'm not sure how this will be administered. It may still be administered over, certainly you'll have more time to do this because it'll probably have more questions than the other exams did. So we may either give you an extra period to do it, or perhaps it will actually be broken up into two exams. Right now, I don't know, so I can't really answer that, but it will be, it will certainly be announced to you in advance. Thank you for your attention.